Hi students, and welcome to another video lecture on logic design. To get started with this video, let us do a quick revision on the full adder. This is a block diagram of a full adder. Recollect that a full adder has three inputs A, B and C in. Also, it has two outputs S and C out, which stands for sum and carry output respectively. So in conclusion, a full adder is expected to add 3 bits. But what if we want to use full adders to add two binary numbers? How many do we need? For example, let the first number be 1011 and the second number be 1111. The goal is to add these two numbers using full adder. Let us take the first column. So since the first column is made up of 2 bits, I can use 1/2 adder to do the addition. Recollect that the half adder can add just 2 bits. So we get this sum as 0 and there is a carry of 1. Now observe this next column. It is made up of 3 bits. So obviously to add this column I would require a full adder since there are 3 bits to add. Adding this column we get the sum of 1 and a carry of 1. Similarly, to add the next column I would also require a full adder. Adding that column, you will get the sum of 0 and a carry of 1. Similarly, to add the last column, I would also require one more full adder to get the sum of 1 and a carry of 1. This is the final sum. Hence, we can conclude that to add a 4-bit number, we require 1/2 adder and 3 full adders. However, if we make this modification to the full adder, that is, we ground the value of C in, essentially making a full adder to behave like a half adder by forcing it to add just 2 bits A and B. We can now revise our conclusion that to add 2 4-bit numbers, we can use 4 full adders. We can generalize and say that to add n-bit binary numbers, we require n full adders. Going back to our example of these 4-bit numbers. As I said, we require 4 full adders to do the job. Let us begin to draw the block diagram. To add the first column, we need a full adder such that the third input bit is grounded. Observe the naming nomenclature that is used. This full adder is labeled as FA0 and it has the inputs A0 and B0. The third input CN0 is grounded. It also has 2 outputs labeled as S0 and Cout0, which is short form for sum and carry out respectively. To add the second column, we need another full adder. Observe the naming nomenclature again. The full adder is named FA1 and has 3 inputs A1, B1 and C in 1. Note that C in 1 is connected to Cout0 from the previous full adder. This full adder also has 2 outputs S1 and Cout1. To add the third column, we need another full adder. Observe the naming nomenclature again. This full adder is named as FA2 and has 3 inputs A2, B2 and Cn2. Note that Cin2 is connected to Cout1 from the previous full adder. This full adder also has two outputs, S2 and Cout2. To add the fourth column, we need another full adder. The naming nomenclature is, this full adder is named as FA3 and has three inputs, A3, B3 and Cin3. Note that Cin3 is connected to Cout2 from the previous full adder. This full adder also has two outputs, S3 and Cout3. Such a collection of adders connected together is called ripple carry adder. This is because the carry out from each stage is connected to the carry in of the next stage. Also notice that the sum and carry out bits of any stage cannot be produced until after some time that the carry in of that stage occurs. For example, take the full adder FA1. The outputs S1 and Cout1 are not valid until after getting the inputs Cin1, which is connected to Cout0. Similarly, for full adder FA2, the outputs S2 and Cout2 are not valid until after getting Cin2, which is connected to Cout1. The same is for full adder FA3. This delay in getting the answer is called as carry propagation delay, and it happens since the carry bits must propagate or ripple through all the stages before the sum bits are valid. This is a major disadvantage of the ripple carry adder. An adder that speeds up the process of addition by eliminating ripple carry delay is called as the look-ahead carry adder. This particular carry adder examines all the input bits simultaneously and also generates the carry-in bits for all the stages. The method of speeding up the addition process is based on two additional functions of the full adder: carry generate, which we will nickname as CG, and carry propagate, which we will call as CP. Let us take a look at the carry generate function. The carry generate function indicates when a carry out would be generated by a full adder. A carry out is generated only when both the inputs A and B are 1. Recollect the truth table for a full adder. The only two entries in this table where both inputs A and B are 1 and generate a carry are as follows. In the first case, A and B are 1, so we get a carry out as 1. In the second case, A and B are 1, so we also get a carry out, or in other words, a carry is generated. So we can conclude that CG is equal to A and B, denoted as A dot B. Now let's take a look at carry propagate. A carry may be propagated in a full adder when either or both inputs A and B are 1. Based on this definition and using a reference to the truth table of a full adder, we can see carry propagate in these cases. We look for all those cases where A or B are a 1 and a carry out is generated. We get 4 such cases. This is the first one, second, third, and the fourth. Therefore, we can conclude that carry propagate or CP is A plus B. Recollect the equations of a full adder. A full adder has two outputs, sum, which is denoted as S and is equal to A XOR B XOR C, and carry out, which is denoted as C out, which is equal to A XOR B dot C plus A dot B. From the previous slide, we know that carry generate is equal to A dot B and carry propagate is equal to A plus B. Substituting these values in the equation for carry out, we get the following. Carry out is equal to Cp dot Cin plus Cg. I will just rearrange the terms to make the equation look like this. So what we have done here is expressed carry out in this case not in terms of the inputs A and B, but in terms of the function Cg and Cp, which will considerably reduce carry propagation delay. Hence, we can now calculate the following. For full adder 0, we can say C out 0 is equal to carry generate 0 or Cg 0 plus Cp 0 into Cin 0. For full adder 1, we can say Cin 1 is equal to C out 0 and C out 1 will be equal to Cg1 plus Cp1 into Cn1. But you know that Cn1 is equal to C out 0. Thus the equation can be rearranged as Cg1 plus Cp1 into C out 0. Substitute the value of C out 0 and open out the brackets. We get the equation as follows. In the same way, for full adder 2, Cin2 is equal to C out 1 and C out 2 is equal to Cg2 plus Cp2 into Cin2. But you know that Cin2 is equal to C out 1. Thus the equation now becomes Cg2 plus Cp2 into C out 1. We'll substitute the value of C out 1 and open out the brackets. In the same way, we can calculate for full adder 3. Cin3 is equal to C out 2 and C out 3 is equal to Cg3 plus Cp3 into Cin3. But you know that Cin3 is equal to C out 2 and thus the equation becomes Cg3 plus Cp3 into C out 2. We'll substitute the value of C out 2 and open out the brackets. If you observe all these equations that we have just calculated, you will notice that the carry out of each full adder stage is dependent only on the initial carry, that is Cn0. And note that each of the Cg and Cp functions can be expressed in terms of inputs A and B. All of the output carries are immediately available and there is no need to wait for a carry to ripple through all of the stages to get to the final answer. That's all for now. Connect to the classroom for more videos and study material.